2023 National Electrical Code, or NEC, has specific requirements for grounding electrodes, particularly regarding metal water piping systems. Section 250.52 ATWO addresses metal water piping systems. It states that if a metal water piping system is in direct contact with the earth for 10 feet or more, it is considered an effective grounding electrode. However, Section 250.52 A3 clarifies that if the water pipe is isolated from the earth by a non-conductive coating or plastic pipe, it is not considered an effective grounding electrode. This distinction is crucial for understanding the requirements for grounding electrodes in various situations. If the water supply pipe is not in direct contact with the earth for at least 10 feet, or if it is isolated by a non-conductive coating or plastic pipe, it cannot be used as the sole grounding electrode. In such cases, an additional grounding electrode is required. This additional electrode is commonly a ground rod. The ground rod must be at least 8 feet long and driven into the earth. The NEC also specifies requirements for the impedance to ground of grounding electrodes. According to NEC 250.56 AN, the combined impedance to ground of all grounding electrodes must be less than 25 ohms. If the impedance is higher than 25 ohms, additional grounding electrodes may be required. This could involve installing additional ground rods or improving the connection to existing electrodes. There are several steps to take to ensure compliance with the NEC grounding electrode requirements. Firstly, check the impedance to ground of the existing ground rod and the connection to the water supply pipe, if applicable. If the impedance is more than 25 ohms, an additional ground rod should be installed. This additional ground rod must be at least 8 feet apart from the existing rod. Ensure that the ground rods are properly driven into the earth and connected to the grounding bus in the service panel with a grounding electrode conductor. It is recommended to contact the power company to schedule an electrical inspection once the grounding system is complete to ensure compliance with all applicable codes and regulations. The grounding electrode conductor, or GEC, is used to connect the grounding electrode to the equipment grounding busbar in the electrical panel. Its size is determined by NEC Table 250.66, which bases the conductor size on the size of the ungrounded service entrance conductors. For example, if the service entrance conductors are 2/0 copper, the minimum size GEC would be number 4 copper. If the service entrance conductors are 3/0 aluminum, the minimum size GEC would also be number 4 copper. When multiple grounding electrodes are used, they must be bonded together to form a grounding electrode system. This bonding ensures that all electrodes are at the same potential, reducing the risk of voltage differences and improving the effectiveness of the grounding system. The bonding jumper used to connect the electrodes must be sized according to NEC Table 250.66, similar to the grounding electrode conductor. The location of the grounding electrodes is also important. Ground rods should be driven into the earth as close as possible to the service entrance. The NEC requires that ground rods be at least 8 feet long and driven vertically into the ground. If rock bottom is encountered, the rod can be buried at an angle not exceeding 45 degrees from vertical or laid horizontally in a trench at least 30 inches deep. The spacing between ground rods is also crucial. The NEC recommends that ground rods be spaced at least 6 feet apart. This spacing helps to ensure that each rod is in a different area of earth, providing a more effective grounding path. The connection of the grounding electrode conductor to the ground rod is critical. The connection must be made using listed grounding clamp-jaw connectors. These connectors are designed to provide a reliable, low-impedance connection that will withstand corrosion and mechanical stress. The NEC also addresses the use of concrete-encased electrodes, often referred to as UFA grounds. A concrete-encased electrode consists of at least 20 feet of bare copper conductor that is encased in concrete. The conductor must be at least number 4 American wire gauge, OG, in size and must be located within the concrete near the bottom of a foundation or footing that is in direct contact with the earth. Concrete encased electrodes are very effective grounding electrodes and are often used in new construction. In addition to ground rods and concrete encased electrodes, other types of grounding electrodes are permitted by the NEC, including ground rings and plate electrodes. A ground ring consists of a bare copper conductor that is buried in a continuous loop around a building. The conductor must be at least number 2 AWG in size and must be buried at a depth of at least 30 inches. Plate electrodes are made of metal and have a surface area of at least 2 square feet. They must be buried at a depth of at least 30 inches. The NEC also addresses the grounding of interior metal water piping systems. Interior metal water piping systems that are likely to become energized must be bonded to the grounding electrode system. This bonding helps to ensure that the piping system is at the same potential as the earth, reducing the risk of electric shock. The bonding conductor must be sized according to NEC Table 250.102 current and must be connected to the piping system using listed bonding clamps or connectors. It is important to note that the NEC is a minimum standard and that local codes may have additional requirements. It is always best to check with the local authority having jurisdiction to ensure compliance with all applicable codes and regulations. Improper grounding can have serious consequences, including electric shock, fire, and equipment damage. It is essential to understand the NEC requirements for grounding electrodes and to follow them carefully. A qualified electrician should always be consulted for any electrical work to ensure that it is done safely and correctly. Regarding impedance, a low impedance ground path is crucial for the proper operation of overcurrent protective devices, such as circuit breakers and fuses. When a fault occurs, a low impedance ground path allows a large amount of current to flow back to the source, causing the overcurrent protective device to trip and de-energize the circuit. If the impedance of the ground path is too high, a fault current may not be high enough to trip the overcurrent protective device, creating a dangerous situation. The NEC provides guidelines for testing the impedance of the grounding system. These tests are typically performed using a ground impedance tester, which measures the impedance between the grounding electrode and the electrical system. If the impedance is found to be too high, corrective action must be taken to reduce it. This may involve installing additional grounding electrodes, improving the connections to existing electrodes, or replacing corroded or damaged grounding conductors. The NEC also addresses the grounding of sensitive electronic equipment. Sensitive electronic equipment, such as computers and medical equipment, can be susceptible to damage from voltage transients and electrical noise. To protect this equipment, it is important to provide a clean, low-impedance ground path. This can be achieved by installing a dedicated grounding electrode system for the sensitive equipment. The dedicated grounding electrode system should be isolated from the building's main grounding electrode system to prevent electrical noise from being introduced. In addition to grounding, bonding is another important aspect of electrical safety. Bonding is the process of connecting all metal parts of an electrical system together to create a common electrical potential. This includes metal conduits, metal enclosures, metal piping systems, and metal equipment frames. Bonding helps to reduce the risk of electric shock by ensuring that all metal parts are at the same potential. The bonding conductors must be sized according to NEC Table 250.102 current and must be connected to the metal parts using listed bonding clamps or connectors. The NEC also addresses the use of surge protective devices, or SPDs. SPD are designed to protect electrical equipment from voltage surges caused by lightning, utility switching, and other events. SPD are connected to the electrical system in parallel with the equipment they are protecting. When a voltage surge occurs, the SPD diverts the surge current to ground, protecting the equipment from damage. SPD should be installed at the service entrance and at branch circuits feeding sensitive electronic equipment. The NEC provides guidelines for the selection and installation of SPD. It is important to choose an SPD that is rated for the voltage and current of the electrical system. The SPD should be installed in accordance with the manufacturer's instructions and should be properly grounded. The NEC also addresses the grounding of separately derived systems. A separately derived system is an electrical system that is powered by a source other than the utility grid, such as a generator or a transformer. Separately derived systems must be grounded in accordance with NEC Section 250.30. The grounding requirements for separately derived systems are similar to those for service entrances. A grounding electrode system must be installed and connected to the system neutral point. The size of the grounding electrode conductor must be determined according to NEC Table 250.66. The NEC also addresses the grounding of equipment. All electrical equipment that is likely to become energized must be grounded. This includes equipment such as motors, appliances, and lighting fixtures. Grounding helps to protect against electric shock by providing a low impedance path for fault current to flow back to the source. The equipment grounding conductor must be sized according to NEC Table 250.122 and must be connected to the equipment grounding terminal. The NEC also addresses the use of ground fault circuit interrupters, or GFCIs. GFCIs are designed to protect against electric shock by detecting small amounts of current leakage to ground. When a GFCI detects current leakage, it quickly interrupts the circuit, preventing electric shock. GFCIs are required in many locations, including bathrooms, kitchens, and outdoor areas. The NEC provides guidelines for the installation and testing of GFCIs. It is important to test GFCIs regularly to ensure that they are functioning properly. The testing can be done by pressing the test button on the GFCI. If the GFCI does not trip when the test button is pressed, it should be replaced. The NEC also addresses the use of arc fault circuit interrupters, or AFCIs. AFCIs are designed to protect against fires caused by arcing faults. Arcing faults are a type of electrical fault that can occur when electricity jumps between two conductors. AFCIs detect arcing faults and quickly interrupt the circuit, preventing a fire. AFCIs are required in many locations, including bedrooms and living rooms. The NEC provides guidelines for the installation and testing of AFCIs. It is important to test AFCIs regularly to ensure that they are functioning properly. In summary, proper grounding is essential for electrical safety. The NEC provides detailed requirements for grounding electrodes, grounding conductors, bonding, surge protection, and ground fault protection. It is important to understand these requirements and to follow them carefully. A qualified electrician should always be consulted for any electrical work to ensure that it is done safely and correctly.